Hey guys, welcome back. There's always a delay, so I never know should I start talking yet. So I always peek up in the corner and say that I'm recording. So then I start talking. Um, I'll get used to it. No, I won't. Hey, this is chapter 3, lecture 2. You watched lecture 1. We got a little technical, okay? We're gonna get more technical. Talking about plasma membranes. They're a big deal to me. I don't know, maybe some people not so much. So in our last lecture, which I just did because I'm wearing the same shirt if you didn't notice, we talked about that there's different types of cells based on form and function. We have a lot of cell specialization in the body. The cell is the basic unit of life, considered a living thing. If you're smaller than a cell, you're not considered alive. And then the plasma membrane, the outer barrier of the cell. We're not going to talk about organelles. We're not going to talk about cytoplasm. We're not going to talk about nucleus or chromosomes or chromatin or blah, blah, blah. But we're talking about the plasma membrane. The components were that phospholipid bilayer, that cholesterol, integral proteins, which went across the cell, peripheral proteins either on the inside or the outside of the cell. We talked about glycoproteins, glycolipids also being present in there. The glycolipids, glycoproteins with those carbohydrates, that sugary coat is the glycocalyx. And we said, what's the deal? What can pass through, what can't? Oxygen, carbon dioxide can pass, no problem. Water can pass. I think we didn't even mention about water. Water is polar. Water is tricky. We can't control water. We have to trick water because water is a big deal to manage. We have tons of mechanisms to manage water in our body and just kind of understanding water. So the movement of water is kooky. So we're actually going to talk about that this lecture, the movement of water. So, hey, I'm just doing it on the fly. I figure, hey, my lectures are my lectures. There's plenty of other parts of Chapter 3 on Wiley Plus that you have to work through. And this is just a supplement, so I'm not too concerned if it's not perfect. Sorry, guys. I'm not perfect by any means. Maybe you are. I am not. All right. We left off with this crazy slide, and you see, like I said, I'm still sitting here. I'm going to do the next lecture. Or not. Okay. So the first thing I want to talk about is this crazy concept of using the plasma membrane, using the fact that it is a barrier to do work in the cell. So I do work in the cell by moving things, maybe not where they want to go. And I can make a gradient. So a gradient, this word gradient here means that there is a difference in number. How about amount? Outside the cell versus inside the cell. Okay, that's the deal with the gradient. I can do a concentration gradient by taking a chemical and having it be more quantity on one side of the plasma membrane. Okay, so a concentration gradient is a chemical. I can do an electrical gradient, and that means that I have a difference in the concentration of an ion on one side or the other because ions have a charge. And because ions have a charge, that has to do with like electrical impulses, electrical signaling. It's all based on ions. And so if I take a cell, here's my little cell. Of course, it's going to give me these other error messages. And I say, hey, I'm going to pump more sodium outside than inside, okay? The sodium part is chemical, but that sodium ion also has a plus charge. So on the outside, outside cell, more sodium. equals chemical, but then it's also more plus charge, more of that plus. That's supposed to be a plus, right? Because sodium had a plus, and that's electrical. And together, it's an electrochemical gradient, and that's what our cells do. We make sure there's more sodium on the outside, and that's a potential. It's a potential to do work. It's a potential in electrical definitions. I'm not going there, but that's known as the membrane potential. It's usually an extra credit question on the test, is the fact that there's more of a charge on the outside, on one side of the cell, and more of a chemical on one side of the cell, either outside or inside. So that kind of leads us into transport. And we're going to talk about, there's two different types of transport. We're going to talk about passive transport in this lecture, and then we'll do different active processes in the next lecture. So we got some stuff to talk about today, but it's good, and it should make sense. It's really my deal, because we have to have transport in order for our cells to, where's my pen? Here it is, to, well, critical to the life of the cell. I have to move things in for chemical reactions. Chemical reactions is my cell metabolism, making ATP, making nutrients, making proteins, and I need to get rid of waste. They have to move out of the cell, as if I hold on to them, they're toxic. Waste is toxic to the cell. So it has to get the heck out of there. All right. So cell movement, cell transport is either passive, meaning it just moves on its own. How does it move on its own? Oops, I'm very distracted. Squirrel. It moves on its own because it moves along, where did my pen go? Hey, oh, there it is. It moves along a concentration gradient. Oh, that's supposed to be the word concentration. Okay, moves from where there's more, high concentration, to where there's less. So moves from more to less of a chemical or electrical concentration. We'll talk about that in a second. The other type of movement in the cell is active, and active means I use ATP. ATP is my only energy source in the body. How do I make ATP? I need glucose and I need oxygen, hopefully. But ATP is what drives these processes and powers them up. And this is, why do I need to do that? Well, if I'm moving big things, I need ATP. Big things. If I have to move something against its gradient, oh, hey, I don't want to go there. You're making me go there. So this means if I'm moving something from low concentration, these little brackets mean concentration, to high concentration, that will also require ATP, low to high. So it's opposite from, remember, passive. I want to move there. It's like going downstream. This is like going upstream. This is like, how many people can I cram into a telephone booth, which I don't even think those things exist anymore. So I need a new example. Well, things that change in 10 years. It's very funny. All right, 11 years. Yeah. Okay. So we're going to be talking about passive forms of transport. There's three. Actually, there's four, because there's two different types of facilitated diffusion. Active means that it moves, uses ATP. Right? Passive means no ATP. Moves along a concentration gradient. I know we just talked about this in the last slide, but I really want to drive that point home. How that works. And when I say that it moves along a concentration gradient, it goes from high to low. Okay, so we're just going to focus on these three today. Simple diffusion, like oxygen, carbon dioxide, that's how those guys move in the body. Facilitated diffusion, like how ions and nutrients move. And then osmosis. Osmosis is going to be the one that makes your head blow up. And that is the movement of water. Okie dokie. Did you hear my stomach growl? It was really loud. Snack time. All right. So do you see how the slide is a video? You can access the PowerPoint and watch the video. That's not what I'm going to do. Okay. So passive transport means that it moves from where there's more into where there's less until it's equal. Equilibrium means equal amounts on, I'm getting excited and I'm pressing too hard on the pen. Oh, son of a biscuit. Equal amounts on both sides of cell, outside and inside. Out and in. Okay. It will continue to move randomly. Okay. So I'm going to go back to this. So if this is a room, I just had a peek. Okay. Here's our little room. And I'm standing right here and I spray perfume. Right here. Well, this perfume is all these little chemicals, and what they do is they bounce around each other. That's this kinetic energy. They bounce around and they spread out until eventually you right here, this is you. I'm going to give you a happy face. I'll even give you a little hair. Eventually you can smell it here. All right, I guess you need a body too, right? And it's moved because of kinetic energy. So kinetic energy is just random collisions. Random collisions means I just keep bumping into each other until we're equally spaced out. To equally space out. I'll just leave it at that. Equally space out. Right? That's simple diffusion. Oh, that's simple diffusion, this slide. So this was all the drawing and all the words is the example for simple diffusion, which was the first type of a passive transport, which was actually the next slide. I'm going to come back. Oh, okay. I just had a peek. All right. All righty. So this one was here. I want to talk about all of these because these are uber important. This one here is I put a chemical in the bottom of this beaker. I filled the beaker up with water and I just sit it on the table. So as time goes by, so time is passing between beginning and end, these particles start to bounce around. And then they're totally equally spread out in this whole contained volume. All right, that's my simple diffusion. It's just random collisions. And certain things in your body do move by diffusion. You want to know something that does scary and crazy? Oxygen. Oxygen depends on diffusion. Whoa. Carbon dioxide depends on diffusion. Okay, these are big deal things. And when you think of diffusion, you don't really think that it's fast, right? That perfume didn't just happen immediately and get over to you on the other side of the room. But then diffusion, so diffusion, the rate of diffusion, how quickly something can diffuse, has all of these inputs. Rate of diffusion is based on what's the difference from the outside to the inside? The steepness of the concentration gradient. That would be the difference on both sides. If it's not that great of a difference, it's going to diffuse slower. What's the temperature? So when you're looking at these, you want to give an example. You want to understand it's not just temperature affects the rate of diffusion, but if it's hotter, you heat will make it go faster. Cold will make it move slower, right? So everything's slower in the cold. So it's understanding, right? More will go faster. I'll just do an F for, all right, that's horrible. I'll spell it out. Less will make it go slower. The mass, how big is the particle? Let me write it over here. So it's size. Mass is size, okay? Obviously, big will be slower. And small, those little small boogers, will be faster. Ask anybody around a 2-year-old versus an 80-year-old, right? Oh, no, not a 2-year-old, a little small guy versus a larger size. And that's in the lab on Friday. So, well, you'll see videos about it in the lab. That's covered in this week. The other factor that affects the rate of diffusion is surface area. Surface area is the area, the size of the area that something can diffuse across. Ooh. Can go across. So what that means is, I'm a red blood cell that has this awesome biconcave shape, versus if I'm a red blood cell that's just a circle, this guy, right? So these were little red blood cells. This one's a sad red blood cell. This guy has a whole lot of room for oxygen to go into the red blood cell, so it has increased surface area. And this, if it's just a straight up little circle, has less surface area. So there's not as much space for oxygen to cross. So if I have increased surface area, if I have more, I can get more things across. So surface area is a huge strategy used in the body because so many ridiculously important things depend on simple diffusion. Okay, and the other one is, well, let's go back to this. So increased surface area, it means faster. Decreased surface area means slower. Oops. And then the other one is how far to go, diffusion distance, right? How far do you need to go? Nerve impulses depend on diffusion. I can't believe it, right? I go to pick up a pencil, it's instantaneous. And you know what? This happened on many different steps that involved diffusion. Diffusion of neurotransmitter, diffusion of calcium for muscle contraction. I mean, it's just nuts, diffusion. But the space, right, that something has to diffuse across is super teeny weeny. So therefore, if it's a smaller distance, it'll be quicker. Now, the other one, there's actually a number 6 here. I know, I keep forgetting to add it to the slides. I suck. Is what is my environment? If you think about oxygen, oxygen's in the air. Air is a gas, and it has to cross into a liquid environment, right? If you think of me, and I'm running on the beach in my little bathing suit, and I love beach watching people, and I love watching the joggers run on the beach, and they look awesome, right? And you're like, oh yeah, they got it all together, they're so fit. If I then, it's not really me, so I shouldn't say me. If they then go to run in the water, are they going to look that awesome? No, because water has, the properties of slowing them down. So is my environment air, gas? Oh, I lost my little black dot. Here it is. Is it, a gaseous environment like air? Is it a liquid environment like inside the body? That is also something, well, when we factor in cold, it's not like you're going to be diffusing through solid anywhere in the body, so I'm not going to go there. So simple diffusion, I just give you all these crazy examples of nerve impulses and muscle contractions and all sorts of things, oxygen, respiration, all depend on diffusion. So it's actually a huge deal. Passive transport, so no ATP, and then we had all these factors that affect the rate of diffusion. So it's going through the membrane. Of course, I don't have anything to say to that. There's two more passive forms of things, not water, things like ions that have to pass pass across the membrane. So I'm going to go to this picture here, but the last guy there had all the words. So if I have, this is outside the cell, so extracellular fluid means outside cell. Intracellular, so this would be inside cell. Because it's intracellular, might as well use those words a little bit. Okay, so simple diffusion, it just crosses right through the membrane, and things that do simple diffusion across the plasma membrane is oxygen and carbon dioxide. Those are the main ones. Oh yeah, and the little steroid hormones, they can just pass through. Now, we're not going to go into other types of diffusion with those other examples of muscle contractions, so we're not ready for that yet. That's the second half of Bio 158. Now, if I have these, remember these guys? So this was my phospholipid bilayer. We just talked about that last lecture. And then I had these integral proteins, right? These are two different types. Integral means they go from the outside to the inside. One of them is just going to be a channel mediated, and it's just a pore, so it's like a hole. It makes a hole in the phospholipid bilayer, and this item can just go through. Oh, that's not so pretty. Ions travel through channel mediated. So this diffusion, okay? Diffusion is all passive. It's helped, so it's facilitated. That means that there's a helper. So if you see, I actually have two different types of helper. So this is also a helper. Well, we're going to call helper passive movement. I have channel mediated, meaning it's just a pore and things can go. I do funny things with these channels. I'm not ready to tell you what, but I gate them. I close them so they only open at certain times. And the other one is carrier mediated. So carrier mediated means this is like glucose and other nutrients. Right? We need glucose to make ATP to do work constantly. So I'm always going to talk about glucose. Right? So glucose is on the outside of the cell, gets dumped off into this extracellular fluid, and then it goes and it kind of binds it. It seats in. And what happens, I don't want to talk about that. All right, I want to go to this one. So it came in and it bound, and once, so this is carrier mediated. We'll go back to that other one in a minute. Carrier mediated diffusion. Once it binds, this glucose, this purple guy, will bind to the transporter. Look, the transporter changed shape. Okay, transporter changes shape. And lets in, well, actually it brings in the glucose. So do you see it went, kind of went up this way, and then it changed shape and went open the other direction. Oh, nope, I'm not ready for that guy yet. Oops. And then the glucose is released inside the cell. Uh-oh. Husband telling me doesn't know I'm recording, so you're going to get to listen to him. Now, this was my channel. So this was channel mediated. Not you. channel mediated, facilitated, crap, I spelled that wrong. Facilitated diffusion. So stuff can, so this is saying, all right, potassium's inside the cell. It wants to go outside the cell, so it'll go through this integral protein. That's a channel. Right, integral protein. Oh, I thought I heard him. But I have a gate on it. So see, I control my channels with gates. Controls when things move. Not what moves. Oh, yeah, they're usually different channels. When things move. Because I only want potassium to move at certain times. All right, so we had I went backwards. Simple diffusion, channel mediated, and carrier mediated facilitated diffusion. So here's a little bit more about channel mediated. Here's a little bit more about carrier mediated. Right? So those are my three main types of passive transport, right? Passive transport, no ATP. Moving along concentration gradient, going from where there's more to where there's less. And because I have this phospholipid bilayer, I need these channels to get other things into and out of the cell. And they can either be, so I have simple diffusion. I'm just writing it over. I have channel mediated, facilitated diffusion, still passive, still no ATP, right? This thing changes shape. I have gates, still not using ATP, or carrier mediated. Facilitated diffusion. I'm not going to write it all out. You've heard me talk about it for like the past half hour. The third type of passive transport, let me take a drink, I'm going to need some. It's only water, sorry guys, I'm not that interesting. Is the movement of water. Water is osmosis. And I'm going to peek for a second. I hate all these things. Okay. Yep. Okay, a couple slides left. There, I see all these words and I kind of cringe because it's not how I want you to think about water. We can't control water. Water moves. So it's like, okay, here, water moves from where there's more water to where there's less water. Blah, 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 blah. All membranes are permeable to water. I don't even want to talk about hydrostatic and osmotic pressures. Yuck. So let's just go, ugh, that's kind of yucky. And yeah, this is yucky too. I want to talk about water in a living environment. So, I really just want to talk about this slide. And it already gives you the answers and that pisses me off. But I am not going to go with these pictures. So there's a couple like golden rules. Water follows salt. So everyone's like, okay, water follows salt. Well, water follows salt, water follows glucose. What I say is water goes to the party. And the party is like, where is it happening? Where is there more stuff? Okay, those are kind of my technical rules for the movement of water. Goes to the party. Where's the party? So, I'm not really looking at these pictures right now. I guess I should, though. Let's start at this end. Okay. So, I know this is already all drawn up here, but I'm not happy with it. If I take a solution and let me draw all my boxes. Of course, that means I ran out of room to do all my writing. Right, so all of these are like the beakers that are drawn ahead. And my little circle is my cell. And my cell always has 0.9% stuff in it. Okay? That's what cells are. They're 0.9%, 0.9%. They're 0.9%. Okay, so far you're with me. Oh, and you're like, what was that circle? This circle, again, was a cell. Okay, I'm not going to label it on all of them, but that's what it is. Cell with 0.9% of stuff. That's the concentration of a cell, 0.9%. If I put it in straight water, a beaker, so this is obviously a beaker, so okay, I said I wasn't going to label it in here. I'm labeling it, and this is a beaker. If this beaker is just straight up deionized, no. Oh, son of a biscuit. Hold on. Okay, it's still there. I move things up. I think I'm cramping my stove. Straight up deionized water. Deionized water means that there's nothing else. It's 0% stuff. Okay. Where will water? So it's just water. Deionized water is just water. No, nothing else. That's supposed to be a percentage. Where does water want to go? Well, water wants to go where the party is, and the party is inside the cell. So water will go into the cell. So when you look at all these diagrams, it's always like, understand what's happening, and it's a numbers game. Where is there more? Okay, more is inside the cell. If more is inside the cell, water will move in. Water enters. Okay, so this is a picture of water entering into the cell. So that's 1. What happens to the cell is 2. The cell bursts. And the fancy name for burst is hemolysis. Okay, that's that word there that I tried to write, and it's not very pretty. And because there is less stuff on the outside is a hypotonic solution. So deionized water is a hypotonic solution. That means there's less stuff outside. As long as outside is less than what's inside the cell, it's hypotonic. So even if it was 0.7%, right? 0.7 is less than 0.9, right? That would still be hypotonic. So don't get hung up or totally married to the fact that it was 0. It just had to be less than 0.9. All right, so that's hypotonic. Hypotonic. And you can't control water. So I want to talk a little bit more about this after I go through these. Oh my gosh, I've been talking for a while though. I'll do it in lab when I see you guys on Friday. The other situation is, say I have more stuff, okay? If I have 10% of a salt on the outside and in the cell inside is 0.9, where does water want to go? Water wants to go to the party, and I would rather have $10 than 90 cents too. So I'd be like, oh, I'm going with the guy that has $10. So water leaves the cell. If water leaves the cell, and that's what this picture is saying, the cell shrivels. And the fancy name for shrivels is crenate. Yeah, that's supposed to be the letter N. And that solution, because there's more outside, that's supposed to be an R. It's hypertonic, okay? So that's the, nope, U. The third thing is, so 1 is look at the numbers. 2, figure out where water goes. Water leaves the cell. 3, what happens to the cell? Cell shrivels. 4, what is it called? Hypertonic solution. So the last one that we have is isotonic, okay? So iso means same. So that means that it must be 0.9% on the outside of the cell because that's the same. Does water move? Yeah, water always moves. It's just that water moves in and water moves out at the same rate. So this is showing you water in and out at same rate. 1 in, 1 out. What happens to the cell? Nothing. Cell stays normal. No change in cell shape. If there's no change in the cell shape, that means it's an isotonic solution because the numbers are the same. and the cell gets to live happily ever after. I know I've been talking for 35 minutes. I feel really, really bad, but you have your body cells. Right? You have your blood vessel. Let's just say capillary. And these were body cells. And then you have this space between, there's this interstitial space. If you chug, I'm doing the water challenge and chugging a gallon of water. If you chug a ton of water, it all goes into your bloodstream. It leaves the bloodstream. It enters into your cells. You can't control water if there's a ton. It causes those cells to expand. You go in a coma, you die. Right? You can kill yourself with water. Not by like just drowning either. By dumping too much in your body. And if you're super duper dehydrated, so your blood is super salty, right? Because you're dehydrated, it will pull water out of the cell. Water will leave the cells to then, go be, hey, the part is in the capillary, that's where there's more. And those cells will shrivel, you'll go into a coma and you'll die, right? So you can die from dehydration. You can die from overhydration. It's nuts. So water is scary, and it's a big thing for our body to manage. I love talking about water, obviously. But I am going to call it there because we're not going to start this, and I'm not even going to talk about this today. And I thank you for your time. I could talk about this stuff forever. It's pretty cool. All right. I will see you another time. Bye.